Hi, and welcome to this presentation where I describe a physical model of rate, state, and temperature-dependent friction with multiple healing mechanisms. As an introduction, I will describe some key observations that were essential to constrain the model, and then I will present how they can be explained with simple, few tractable assumptions. Some of the most robust and fundamental observation we have about friction is summarized by this famous paper by Byerlee, is that friction is essentially independent of rock type. And a wide collection of different rocks show coefficient of friction between 0.4 and 0.8, independent of individual strength. So if you consider some of the weakest rocks, for example, the tuff, and some of the strongest one, the basalt or the gabbro, they have essentially the same coefficient of friction. And so that's a little bit puzzling and needs to be explained. But friction goes far beyond just the concept of static strength. And is involved in seismic cycles. So there's a mechanisms for strength drop and strength recovery, so-called healing. And that is explained by also other famous experiments that friction actually recovers at stationary contact with a linear increase in the static coefficient of friction, static quote unquote, with the logarithm of the time of hold. So there's this logarithmic healing going on that allows the seismic cycle. And during seismic cycle, however, we can keep track of the evolution of friction, and that is captured by these laboratory experiments at different sliding velocities. And what we see is that friction always follows a direct effect when the velocity is increased. But this is followed by a time-dependent evolutionary phase where friction can increase or decrease and reach another value at a new steady state. And so this is captured by a state dependence of the friction coefficient that essentially capture the evolution of the texture of the contact, whether it's bare contact between two solids or a gouge layer made of granular material. So what's important about friction, especially for seismic cycles, is that friction depends on the rate of sliding, but also on the history of deformation. And that is captured that can be captured by a state variable. And the state variable seems to be most naturally the evolution, capturing the evolution of so-called contact junctions, which are very small asperities that support the load at the microscopic level. And this was highlighted by some other famous experiments by Dietrich and Kilgore that imaged the distribution and size of these contact junctions in transparent materials. So plastic, sure, but also calcite and quartz. And so it shows that only a very tiny fraction of the true contact area is in true contact with the other side, of the order of a few percent. And so these microasperities bear a lot more load in shear and normal stress than the average values. And these experiments have shown that the true area of contact, in fact, increases with normal stress. But not only this, and if you actually keep these contacts for a long time, you would see them flattening and expanding as a function of time. In addition to that, we see that the size of these microasperities on average seems to find a steady state that is inversely proportional to temperature. So it seems that the area of contact or the size of these microasperities may be the most natural state variable to describe the memory of the system. This is supported by more recent series of experiments that exploits also transparent material and directly image the area of contact through the amount of light transmitted to a transparent material during seismic ruptures. And so we're now capable of seeing the passage of a rupture front at different speeds, from very slow to some approaching the Rayleigh seismic speed, where the area of contact is destroyed by the passage of the rupture. So this is also reinforcing the idea that the state variable, the most physical state variable, may be the area of contact in the gouge or a bare contact between rough surfaces. Some other very fundamental progress in the physics of friction was made by Frederick Chester and collaborators, who show that friction is truly a thermally activated process. And that was demonstrated with these very famous experiments that show how the friction evolves with imposing different sliding velocities. So you see a direct effect and followed by an evolutionary phase. But the effect is almost equivalent when you keep the velocity constant and you impose a different temperature. There's also a direct effect and an evolutionary phase. And so this demonstrated clearly that you can think of friction as a rate state, but also temperature dependent process. And then in the last 2 decades, there's been a wealth of observations of the frictional resistance of different rocks under various hydrothermal conditions. And what these frictional data has been typically, data has been typically explained by a thermally activated process that predicts a linear relationship between this direct effect of velocity, this parameter A, with absolute temperature, implying that this parameter is 0 at 0 degree Kelvin and a finite value at finite temperatures. However, this is not what is observed in many different experiments that actually show a direct effect parameter relatively independent of temperature. So if you look at these examples here for various rocks that are typically found at tectonic plate boundaries, subduction zones, oceanic or continental environments, granite, pyroxene, hornblende, shale, and natural samples from the longitudinal valley fault and the alpine fault. You can see that the direct effect parameter A is relatively independent of temperature for a wide range of temperatures, spanning several hundreds of degrees. What is found instead is that the parameter controlling the evolutionary effects, this B parameter, or A minus B, is a very sensitive function of temperature. A typical behavior is that these rocks are velocity strengthening at low temperature and velocity weakening at higher temperature. And that manifests itself by a transition from A minus B positive at low temperature to A minus B negative at high temperature. And so this is important because not only it can constrain the location of the seismogenic zone at different tectonic plate boundaries, but it can also explain the so-called shallow slip deficit, where you have lower slip amplitude during earthquakes at shallow depth, lower temperature than you have at greater depth, higher temperatures. And so these data remain to be explained, and so we will find different assumptions that can lead us to a physical description of all these observations. And before I move on to a description of the physical model, I want to describe this other important phenomenon that I won't really address today. That is the transition from friction at stationary contact and then low to intermediate sliding velocity to lubrication at high slip velocity, high temperature. And lubrication involves a series of different mechanisms that strongly weaken the contact, and they involve typically thermally activated mechanisms when temperature approaches the solidus of the rocks. So these are partial or full melting, thermal pressurization of existing fluids, or the pressurization of fluids by thermal decomposition of minerals, for example, carbonates liberating carbon dioxide and pressurizing the contact, the formation of silica gel, the coating of minerals by nanoparticles that also lubricate the contact. So all sorts of different physics that are strongly weakening the material, but quite different from the ones that are involved at intermediate slip speeds. I'm going to focus the discussion on intermediate to low sliding velocity and discuss these high temperature, high sliding velocity effects in a different presentation. So I will now describe a series of simple tractable assumptions that can explain all of these observations of the temperature dependence of empirical frictional parameters in the low velocity, intermediate velocity regime. So we start the discussion by considering the fact that the load under normal and shear conditions is borne by these microasperities. This is the so-called adhesion theory that implies that only a small fraction of the nominal area of contact is in true contact for frictional sliding. And so that, if that was the case, that will be described by this simple model, so-called Hertz model, this Hertzian contact, that describes the area of contact of a single spherical asperity under normal stress. This describes an area of contact that scales linearly with the radius of curvature of the sphere and predicts a parallel relationship with normal stress, where the area scales with normal stress to the 2/3. So that goes against the observation of friction that is typically linear with normal stress. And so this theory is not directly applicable. That creates a conundrum that was solved by different investigators that assumed a roughness of the contact, different types of roughness. So in the first model, the contact junction itself was considered rough. So it had an overall radius of curvature, but the sphere was superimposed with a first and second and third level of roughness in kind of a fractal geometry. And the prediction of that model is that the area of contact is almost linear with the normal stress. So it's proportional to normal stress to the 26/7, and very weakly dependent on the initial radius of curvature of the whole contact junction. So it's proportional to the size to the 1/9. In a second model, the contact junctions are considered identical and perfect spheres, but they are in contact with the other side starting from different heights, assuming a long wavelength topography of the surface. And so these initial heights are randomly distributed, and we can look at the average value of the area of contact as a function of the average value of normal stress. And this model now predicts an exactly linear relationship between the area of contact and normal stress, like in friction, and a weak sensitivity to the original size of these spheres. So these are simple N members that have closed form mathematical solutions. And in reality, a gouge layer involves many beads, different size, different shapes, and they're randomly distributed. So we're going to take the substance of these models but derive a more general formulation that captures the weak sensitivity to the overall size of these asperities and the linear relationship with normal stress. So this is done with this formulation where the area of contact is a linear function of normal stress and a very weak function of the size of these contact junctions. And you can think of this size as the local radius of curvature. So it's a function of the normal stress, and this function is a linear function. So there's a constant and a proportionality constants. And so that's the cohesion and the coefficient of friction. And that's divided by the material hardness, chi. And the whole thing is multiplied by this sensitivity to the size, which is raised to a small power that is written m over n. And so we can directly test this formulation against the data for transparent materials collected by Dietrich and Kilgore, where we can fit the material hardness, the friction coefficient, cohesion, and also the power law that controls the sensitivity to the size. In these experiments, the size is actually controlled by the preparation of the samples with different grit numbers. So the higher the grit, the smaller the grain size. And so we can see this linear relationship with normal stress. We can see this higher order sensitivity to the size of the contact junctions. So this is the first assumption of the model. We can then focus our interest to the velocity of sliding in the fault parallel direction. And that's eventually what we care about, how fast the fault will move. Will this be a slow slip event, an earthquake? Will this be creep? Will this be locked? And so the first assumption that we will make is that there is a yield stress that needs to be overcome for sliding to occur. And so we will say that this yield stress is proportional to the real area of contact. And the proportionality coefficient is the material hardness again. So then we can devise a flow law for the velocity of sliding, which is the second expression shown here, where the velocity is proportional to stress to a power times a function of temperature. This function of temperature is an Arrhenius activation with an activation energy Q and a reference temperature T0. And the stress is relative to this yield stress sigma y. So if the stress is larger than sigma y, when it is raised to the power n, the velocity will be incredibly high. And when the stress is lower than sigma y, when you raise that to a power, this velocity will be incredibly low. And so that represents this very huge sensitivity to normal stress of shear stress of the velocity of sliding. So we can think of that, we can compare that to a static yield criterion where sigma y is kind of this hard bound for stress, where the velocity can be really anything along that line. And in comparison, a power law here with a very high power exponent, the higher the power exponent, the higher you approach that vertical line. But it allows stress of any value below or above that sigma y value. And this is illustrated with values from n equals 55 to 150, which are in fact found to fit a lot of different experimental data. So we have an expression for sigma y because it relates with the area of contact, and we have this flow law. So we can now merge these two equations to find a general formulation. And so this is done here. We have this flow law, dependent stress relative to a yield surface. This yield surface is chi A. A is the area of contact, and it's also inversely proportional to the material hardness. So when we combine these two, we find a rate, state, and temperature dependent constitutive relationship for fault slip, where the material hardness, so this inherent property of the material, vanishes. We now have a constitutive law that is relatively independent of material properties, and that explains why rocks, different hardness from very weak to very strong, internal cohesion, would have very similar friction coefficients. And so as a result, we have, if the stress is known, the size of contact junction is known, and the temperature is known, we can predict how fast the fault will slide. But of course, to make the model to allow seismic cycles, we need independent formulations for how the area of contact will evolve, for how the size of contact junctions will evolve. And for that, we need to consider other physics. But as the formulation is a little bit unusual compared to the empirical formulations for rate and state-dependent friction, we can consider a very simple reformulation to put things in perspective. So instead of calculating the velocity of sliding given stress, size, and temperature, we can look at the stress as a function of everything else. When we do that, that's the equation on the lower left, and it predicts stress as a function of velocity, size of contact junctions, and temperature. But it's pretty much C plus mu naught sigma times some terms that are all raised to the power 1 over n. And n is large, and any number raised to a small power converges to unity. So as a kind of extreme example, if you take 1 billion to the power 1 over 60, that's just 1.4. So essentially all these terms down there are close to 1. And so this very complicated time-dependent physical representation is in fact simplifies to at first order to the Coulomb static failure criterion, tau equals C plus mu naught sigma, if you neglect all of these quantities. So that explains why this formulation, this Coulomb failure criterion, is so useful to explain the failure of materials in different conditions. But of course, you need these extra terms to explain seismic cycles, right? And you don't have earthquake cycles if you don't have these time-dependent different velocities, different size of contact junction and temperatures. In addition, these terms may control not only whether you have earthquakes, but also the style of earthquake, like whether you have crack-like or pulse-like ruptures, super shear. So a lot of interesting phenomena come to life because of how these parameters evolve. So to complete the model, we need to understand how these contact junctions evolve over time. And recall that this is very well documented in experiments conducted with transparent material, where we see the evolution of the contact in true stationary contact and fixed imposed velocity, all during dynamic ruptures of spontaneous crack propagation. So this contact truly evolved, and we need to understand why. And so the key to understanding this is that at the micro scale, contact junctions support a normal load, which is imposed by normal stress. But because of their shape, on their sides, they have essentially no stress. So they see a differential of stress with an enormous normal stress because of their small size, and zero stress on the size. And that manifests itself by a deviatoric stress that is 45 degrees from these principal directions. And this deviatoric stress will drive deformation of the contact junctions. And it will start to flow and accommodate that deviatoric stress. And there are multiple ways that this deformation can happen, different micro mechanisms of internal deformation. And the most common one, or universal one, is so-called viscoelastic collapse. So that's basically viscoelastic flow of these contact junctions. And as the material flows under these very high stresses, it will flatten and therefore collapse and increase the contact area and strengthen the macroscopic strength, the macroscopic gouge or contact in the process. So viscoelastic flow can be done by many even nano or microphysical deformation mechanisms, by diffusion creep, dislocation creep, dislocation climb, the motion of defects, etc., etc., etc. So there's a lot of different mechanisms that can accommodate the flow of these contact junctions. And other mechanisms are activated in the presence of water. So as soon as water is involved, dissolution and precipitation of ions can modulate the speed of deformation. And one such mechanism is crack sealing. So it's the precipitation of ions into cracks, and basically close them and strengthen the contact. Crack sealing and crack healing are basically whether ions that were in the rocks precipitate in the cracks, or different ones fill in that space. Another mechanism is so-called pressure solution creep, and that's a very special form of viscoelastic flow, where the material dissolves in highly stressed areas, then dissolve into the fluid phase, which is assumed saturated, and so it immediately forces precipitation somewhere else in areas of low stress. And that also leads to the collapse of these contact junctions. Another mechanism is stress corrosion, and that modulates the speed of the growth of cracks, and so it basically modulates the speed at which deformation happens. And what's interesting about this mechanism is that they are fairly well understood from different experiments. And what's important for us at this level is that we understand their thermal activation. So viscoelastic collapse operates between 50 and 700 kilojoules per mole, sometimes even more, by different mechanisms of grain growth, grain boundary sliding, dislocation creep. Pressure solution creep, so in the presence of water, obviously, operates under much lower temperatures with activation energies between 17 and 75 kilojoules per mole. And the sealing of cracks, or the cementation process, also operate at low activation energies between 35 and 80 kilojoules per mole. And so what it means is that at these low activation energies, the processes will be extremely fast at room temperature. So that's the different thermal activations will depend on the deformation mechanism at the microscale. But there's another layer of complexity, is that even for the same deformation mechanisms, fault zones with different minerals will have different activation energies as well. So for example, if you consider granite and its viscoelastic flow, it will have different activation energies for different constituent minerals. So if you look at phyllosilicates, it's very weak minerals, and so they have activation energy for viscoelastic flow between 28 and 66 kilojoules per mole. Feldspar, it is between 150 and 600 kilojoules per mole, depending on the type of viscoelastic process. Quartz is quite weak, and it will also deform easily with activation energy between 135 and 240. So phyllosilicates like mica, feldspar, and quartz are basic constituents of granite. And so when you consider the thermal activation of friction, you need to consider mechanisms, but also the rock-forming minerals. And we can continue this kind of description. For calcite, the activation energy is between 145 and 250 for viscoelastic flow. Pressure solution creep, it is between 20 and 65 kilojoules per mole for quartz, and between 17 and 25 for granular calcite. So we can think of a range of different deformation mechanisms, a range of different minerals, and that gives us various different activation energies for these different processes. So we want to capture this to understand how the friction evolves with temperature. So to capture these effects, we can devise formulations that fall within the aging law of rate and state friction, or the slip law and number of rate and state friction. The slip law and the aging law have different pros and cons to explain laboratory data. The slip law explains the symmetry observed in the lab for up and down velocity steps. That is not captured as well by the aging law. However, the sleep law cannot explain healing at stationary contact, and that can be captured by the aging law. So there are pros and cons for these two different end members, and we're simply going to consider them both as end members and see how things work. So for the aging law end member, all of the terms are additive, and the evolution law for the size of the asperity incorporates the effect of competing mechanisms. So what do we mean by that is that in the lab, we see that for a finite range of temperature, the empirical frictional properties are fairly constant. So A, B, L, all these are constant finite range of temperature. And then there's another range of temperature for which it is constant, and a gradual transition between the two. And so that means that for these individual range of temperature, the only one mechanism dominates and the other can be neglected. And there's only this very narrow range of temperature where both mechanisms have an interplay and both, have a role on the deformation. So that can be captured by the thermal activation of these mechanisms. And so these laws implement strain rates that are dependent on the temperature through a thermal activation. So let's consider the aging law end member first. So on the left-hand side, you have the rate of change of the size of the contact junctions. And so it is written d dot over d. So the overall physical units is strain rate. And so you can consider all the terms on the right-hand side as different strain rates. So strain rates due to one mechanism or another for the sum of n different healing mechanisms. And on the far right, you have the weakening term that is simply added to represent the contact rejuvenation with sliding velocity. What happens there is essentially contacts are eroded and microasperities disappear and they find another one with more sliding. The process can continue. And the terms in blue are the healing mechanisms. And so they're additive, and whichever has the highest activation will dominate over the other. And you can think of them also as power laws of stress to control strain rate. So what is this strain rate? It is the strain rate of compaction and dilatation. The representative size at this scale is the size of the contact junction, and 1 over this size is basically a strain or a stress. And so this 1 over this size to a power p is essentially a power law of stress. So that's kind of a qualitative interpretation of this formula. So you have a strain rate that depends on the size of the asperity because size controls stress, and that is multiplied by an Arrhenius relationship with an activation energy H and a reference temperature T, or Tk for the mechanism K. So in the aging law end member, all of these terms are additive, and in the sleep law end member, all of these terms are multiplicative. So the strain rates then depend on the log of the product of all of these terms. But the terms are the same otherwise. They are basically found as a simple sum for the aging law, and they are found inside the log for the sleep law. So in general, we find that the sleep law and the aging law have very similar steady state solutions, and they can be made exactly the same by very subtle changes in material properties. So considering the sleep law and the aging law will essentially not change the behavior at steady state for this in this work. So then, to understand how this model works, we can consider the case where only one mechanism dominates. So why is that important if we have many? Well, it's important because within some finite ranges of temperature, that will be the case. One healing mechanism will dominate. And in another range of temperature, another will dominate. And there will be a gradual transition between the two. But if we consider one at a time, we can find closed form solutions and understand the system a little bit better. So if one mechanism dominates, we can neglect the others, and we can look for a steady state solution. So that is given to us by this formulation here with the steady state friction coefficient, which is a function of velocity raised to a power, and to temperature raised to a power. And that power, these powers for velocity and temperature, control whether the system would be velocity weakening, velocity neutral, or velocity strengthening at steady state, or whether it will be temperature hardening, temperature neutral, or temperature weakening at steady state. And so the system, as the system evolves from one dominant healing mechanism to another, we can then see transitions from velocity weakening to velocity strengthening, temperature weakening to temperature strengthening, etc., in various combinations. And so adapting these coefficients and these activation energies for different healing mechanisms will then allow us to capture these gradual transitions in effective frictional properties. So to illustrate this, I make some simple synthetic calculations for material with activation energies for healing of 10 and 80 kilojoule per mole with only 2 healing mechanisms. And in fact, 2 healing mechanisms is what is needed to explain most of the data. And then I calculate the effective frictional properties, so the velocity dependence parameter for the Dirac effect and at steady state, and look at how it evolves with temperature. And so with these parameters, we find a transition from velocity strengthening with A minus B equals 4 10 to the minus 3 at room temperature, transitioning to velocity weakening with A minus B equals minus 4 10 to the minus 3 at 450 degrees, with a transition to velocity neutral at 240 degrees, for example. And that is accompanied with a transition from temperature weakening. You can see that the friction coefficient decreases with higher temperature. Temperature weakening, transitioning to temperature neutral, and then temperature strengthening or temperature hardening in the high temperature regimes. So we can also look at the frictional response under steady loading, simulating a tectonic loading of the fault zone. And so it's basically a spring slider kind of situation. And so the behavior of the spring slider with these constitutive properties will lead to stable creep at room temperature, transitioning to sort of slow slip events at 175 degrees, to firmly stick slip events with increasing stress drops at higher temperatures. So a transition from velocity strengthening to unstable velocity weakening. So basically the model predicts the essence of the various observations that I have shown in the introduction. So then what I do is consider laboratory experiments that document, A, B, L, U, friction coefficient, all these empirical parameters as a function of temperature to determine what are the best thermodynamic properties that will explain these observations. And I do this for various different data sets, different rocks, but I'm only going to show the details for one and then summarize all these observations later. So the one I'm showing to you right now is the laboratory data for wet pyroxene. And pyroxene is an important mineral for the brittle lithosphere, the oceanic lithosphere, but it's also an important mineral for many igneous rocks in a continental setting. So it's kind of an important mineral, rock-forming mineral. And these experiments were conducted by Tian and He, published recently, that show a transition from velocity strengthening at room temperature to velocity weakening at higher temperature. And that can be captured with just 2 healing mechanisms. And you can see that there is a very small variability of the direct effect parameter A. So this can be explained with a constant value that will be the average. A in this model can be approximated by mu naught over n. Using mu naught equals 0.75, that implies an n of 120 also, but there's some variability, plus or minus 40. So a fairly high power exponent for stress. And the transition of the A minus B, so the velocity dependent at steady state parameter, can be explained with two healing mechanisms with activation enthalpy or energies of 25 and 45 kilojoule per mole. So that induces a transition around 200 degrees where it's velocity neutral, and then it's pretty steady behavior for higher temperatures. So these are to fit the parameters that explain laboratory data. The laboratory data are actual time series of the evolution of friction as a function of cumulative slip during velocity jumps. So we can look at this directly. So what we see in these experiments, so these are conducted for velocity downstep. So it's a reduction of velocity from high velocity to low velocity. So in velocity weakening conditions, that would lead to an increase of overall resistance at lower velocity. And in velocity strengthening condition, it would lead to a decrease of frictional strength at lower velocity. So what we see is that at 100 degrees Celsius, the pyroxene is velocity strengthening. At 200 degrees Celsius, it is velocity neutral. And at higher temperature, it is velocity weakening. So it has a higher resistance at lower sliding velocity. And so using an empirical friction law, we could fit all of this data, but we would have to change the constitutive parameters for every little experiment. What the physical model does is that it can consistently explain all of these steps with the same constitutive parameters. So we are reaching a point where a physical model can explain more data at constant parameters than empirical ones. And so we can do this for the aging law n member or the slip law n member. Essentially, if the empirical model of rate and state friction can fit the data, the physical model can as well, except that it can fit the data in other conditions. Notice that the direct effect is smooth in these experiments. It's not like this very sharp jump of friction with the change of velocity. And that's because the apparatus and the sample have a finite stiffness. And so that's actually included in the model, and we use the 100 GPa per meter for all of these steps. In reality, that can actually change during these experiments. So that's for how the model performs to explain wet pyroxene. We can do similar exercise for some other data. For granite, for hornblende, which is a metamorphic phase found in subducting slabs, for shale, and for natural samples from the longitudinal valley fault or the alpine fault in New Zealand. And what we find to explain all of this data is activation energies for the direct effect of temperature between 10 and 50 kilojoule per mole, and power exponents for stress or traction between 55 and 150. So again, much higher than what is found for a viscoelastic environment. So viscoelasticity would have power exponents firmly lower than 20, most often lower than 10, and in the mantle, it will be between 1 and 5. Friction operates at very high power exponents, firmly above 40, sometimes reaching more than 200. So looking at the power exponent is a way to identify whether this is brittle or ductile, right? It can be formulated with the same mathematics, but the parameters are extremely different, and that makes a lot of difference. Second, we can explain the transition from velocity strengthening to velocity weakening using different activation energies for the first and second healing mechanisms in the range of 90 to 130 kilojoule per mole in dry conditions, and in the range of 20 to 65 kilojoule per mole in wet conditions. And that mimics the different types of activation energies found for viscoelastic processes in dry and wet conditions. So we can then compare these empirical fits to velocity step data to the other experiments that were done to precisely identify the activation energies of specific mechanisms. And we find that in dry condition, the healing has activation energies compatible with viscoelastic flow of the minerals forming granite, right? So this mica, this type of phyllosilicate, feldspar, and quartz. So high activation energy. And as soon as there was water in high pressure, we find activation energies for healing that are compatible with various mechanisms that necessitate a fluid environment. So crack healing, cementation, pressure solution creep, and subcritical crack growth, which is the lengthening of cracks towards the tip. And when water is present, subcritical crack growth is modulated by stress corrosions, chemical reactions of dissolutions of the solid phase near the crack tip that sometimes accelerate or slow down the crack propagation. The direct effect of temperature, this activation energy Q, is found to be between 10 and 50 kilojoule per mole. So including values between 10 and 15 that are relatively low. So to me, that explains that some of the deformation happens by athermal processes. So processes for which the activation energy is zero. An example of which is granular flow. So granular flow is a transport mechanism, simply things moving from here to there, does not involve chemical reactions, is not thermally activated. And so some of this granular flow must also be important for frictional sliding. And that means that the effective activation energy can be biased towards low values. And so overall, we found a constitutive framework that can explain the observations and allow us to explain more observations than empirical friction laws can. It also allows us to interpolate laboratory data outside the measurements, so interpolate and extrapolate, and also map out constitutive parameters to actual mechanisms of deformation. So to conclude, I've described a constitutive law for friction that includes the rate, state, and temperature dependence. This is based on the evolution of the real area of contact through the evolution of the size of microasperities at contact junctions, and this size being modulated by different microphysical mechanisms of deformation within the gouge layer. So even though the overall mechanism is brittle, this is friction, it involves microphysical mechanisms that are viscoelastic and time dependent. So this is kind of a fundamental difference. It does not mean that we're describing overall viscoelastic flow in ductile processes. It simply means that the strength of the gouge layer is modulated by time-dependent viscoelastic processes. They can be firmly, dislocation creep, diffusion creep. They can also be fluid-assisted with stress corrosion, pressure solution creep, cementation of cracks, etc. But these microphysical deformation mechanisms modulate the width of the fold zone So they create compaction and dilatancy. They do not accommodate fault parallel shear. And so that's the fundamental difference. So these processes involve healing of the fault zone. And so this formulation explains more data than empirical rate and state-dependent friction laws, and allow extrapolation of laboratory data to identify microphysical mechanisms of deformation based on activation energy, power exponent, and other constitutive parameters. Once again, I want to emphasize that the model is not complete. It does not describe the strong weakening mechanism that happens at high sliding velocity, high temperature approaching the melting point of various minerals. So other physics need to be considered and incorporated to finalize the model, but that represents a framework, a starting point with which we can start to understand how the fault zones deform, and yet it is still applicable to small earthquakes that don't lead to conditions of strong weakening, slow slip events, nucleation, and other parts of the seismic cycle that involve low sliding velocities. So thank you for your attention, and feel free to contact me should you have any question or comments.